Hello and welcome to the course, Design Board Fields with Confidence. This is the second chapter of the sixth part and we will be talking about the MuoviELLIPSE from MuoviTech. Now, the MuoviELLIPSE, it's the younger cousin of the turbo collector, but as the name suggests, it's now an elliptical probe. So it's an elliptical probe with the same counter and counterclockwise rotating fins, with the idea to enhance turbulence at a lower flow rate. And in order to model this type of probe, we basically have to care about two things. So first we have to model the fluid behavior inside of the probe, and that will be again done with computational fluid dynamics and direct numerical simulations, and we discussed that extensively in the last chapter. And again, this is based on the work of Nicholas Hittman, who also did this type of simulations for the elliptical probe with internal fins, the MuoviELLIPSE. But besides the fluid behavior inside the probe, we also have the issue that the probe is no longer circular. It's an irregular shape. And so the heat transfer inside the borehole does also change. And in order to model that, we will use the boundary element method to model this irregular shape. And that method has been inspired and co-developed by Professor Massimo Cimino for the geothermal domain. So let us first take a look at the fluid correlations for this MuoviELLIPSE and then talk about how you can take the heat transfer inside of the borehole into account with the BEM methods. But before we dive into the friction and Nusselt number correlation, we first have to think about what's the diameter of an elliptical probe. Because for a circle that's easy, but if you remember your geometry classes, an ellipse actually has a small and a bigger radius. And the question is, what diameter or what radius do you need to use? And for that, there is this concept of the hydraulic diameter in fluid mechanics. And it's basically a way to convert non-circular pipes into an equivalent circular pipe using the hydraulic diameter, which is defined as 4 times the cross-sectional area divided by the wetted perimeter of this cross-section. And as you can see, for circular probes, this is exactly the diameter, but for elliptical probes, it's slightly smaller due to the ratio of the cross-section between the wetted perimeter. Now, using this diameter, we can define the Reynolds number, and we can actually create graphs for the friction factor and the Nusselt number. And here you see the friction factor correlation for different Reynolds numbers. And again, you see the two analytical solutions. So you see the analytical solution for the laminar case, which is 65 divided by Reynolds. And then you see the Haaland equation for the turbulent solution. And you see here these black dots, these are the solutions for the classical smooth elliptical probe without these fins. And you see that when we add these alternating fins inside the ellipse, that the friction factor increases at a lower flow rate, which is where the turbulence is induced. In this case, that's around 1850 Reynolds number. And when it's above 2300, it follows the exact same structure as with a regular elliptical probe. Now for the Nusselt number, the correlations look like this, and as was the case with the turbo collector, there is a difference made between different Prandtl numbers. If you recall the Prandtl numbers, they also said something about the fluid parameters, more details over in the textbook, but basically the green to the red, it's the range of all the type of antifreezes you have from potassium carbonate, monoethylene glycol, monopropylene glycol, and so forth. And depending on your concentration and which antifreeze you have, you will be either closer to the green line or to the red line. But what you can see here is that we jump away from this laminar range, not at 2300, but at 1850, and then towards 4000 we converge towards the solution of Gnielinski, which is used to model the turbulence in all traditional probes. So these two correlations, again, they tell us everything about the heat transfer inside of the MuoviELLIPSE, but not outside. Therefore, we need the boundary element methods. Now, the boundary element method, we need it because for regular circular pipes, we have an analytical solution, but not for these type of irregular shapes. And that's why we need numerical models to actually calculate the effective borehole tunnel resistance. And that's where we use the boundary element method. So it's basically a numerical method, it's a numerical trick, let's say, for solving linear partial differential equations like our heat transfer equation here. And the way it does that is that instead of solving the heat transfer in a cross section, let's say, between the pipes and the borehole wall, the way it does it is taking the equations for the two-dimensional heat transfer and translating them into equations that work on the pipe walls and the borehole wall. And by doing so, instead of solving basically all the different parts inside the borehole and how the temperature evolves, we only need to solve the boundaries of the pipe and the borehole wall. And more details are over in a textbook, but if you think about it, it's basically like when you have a lake and you put a speaker on the lake and you put sound waves through it. If you want to know how the sound behaves in the lake, what you can do is you can discretize the whole lake and make small water volumes and then simulate that and see how each water volume moves over time, which is extremely computationally intensive. But what you can also do is take that same fluid equation and translate it using green functions to an equation that works on the speaker itself, so on the surface of the lake and of the speaker. And by doing so, you only need to calculate it for a small area, smaller region, which saves you quite a lot of time, and you can take that result and actually say something about the whole lake. So that's the power of the boundary elements method. And the advantage is that you can actually model the real exact geometry of the pipe and get a very accurate result in the end. But as you can imagine, this boundary element method is extremely slow. It's not as slow as solving the heat transfer directly, but it's still way too slow to be used directly into GHG2. And that's why we use an artificial neural network in between. Now, without going too much in detail, the artificial neural network, it's part of the big AI umbrella, and it's basically a model that tries to mimic the way our human brain works. So what it does is it takes certain inputs, and think about it as senses, which are the pipe diameter, the pipe spacing, the borehole diameter, type of grout, etc. It feeds that into the model, where there are different neurons, different layers of neurons, and in the end the model gives us back the internal resistances in the borehole. And just like with a baby that's born, this artificial neural network does not know anything. It needs to be trained. And we train this artificial network with thousands and thousands of this exact boundary element method simulations. And with this trained artificial neural network, it's really fast at simulating or calculating the effective borehole tunnel resistance to a very great accuracy. And that's the approach that's been used to actually simulate it in GHG2. Now here you can see how the boundary element method looks like graphically. So we see our borehole wall as well as our two elliptical shapes, and each of them has a certain number of dots. And these are actually the nodes at which the heat transfer equations are calculated. And each of these nodes also has a certain arrow, two arrows, one perpendicular and one tangent to the object. And these are the two contributions of the heat transfer equations. Now, using the fluid equations and using this boundary element method, let us take a look at the effective borehole tunnel resistance and the pressure drop of the MuoviELLIPSE. So here we once again revisited the question single versus double U-tube, now also compared with a single MuoviELLIPSE. And as you can see, the range in which the single probe outperforms the double one, it increases due to this turbo effect also in this probe. So the Reynolds number for getting turbulence is now 1850, so we can already get this turbulence down to a flow rate of 0.18 liters per second, let's say. And what you can also see that going towards a very turbulent region, that the single DM32 and the MuoviELLIPSE DM32, they have more or less the same borehole resistance, but the single smooth probe is actually ever so slightly better. And that's because, just looking at the geometry, the pipe wall of the circular probe is just slightly closer to the borehole wall. And when you have this turbulence and the heat transfer in the probe is optimized, the only thing that differs is actually the heat transfer through the grout to the borehole wall. And that's exactly ever so slightly smaller with the traditional circular probes than with the MuoviELLIPSE, but it's barely noticeable on the graph here. We also can do the comparison with a slightly bigger diameter for the MuoviELLIPSE and as well as a single smooth DM40. We see here the same story. So the range in which one outperforms the W tube is smaller than before, but now the difference is more significant. So it's way better than the W from between 0.2 to 0.45. And again, here we see that the MuoviELLIPSE increased that range when compared to the traditional smooth probe. But this is not the best we can do, because as said in the beginning, one thing is that this MuoviELLIPSE, it has internal fins to enhance the heat transfer, but due to its shape you can also install it easier in smaller boreholes. And that's why we also compared it to installing the MuoviELLIPSE in a diameter instead of 140 like for the rest, but now in 100 millimeter. And as you can see, there is still quite a lot of room left. We see that due to the fact that our grout resistance reduced so significantly, we now almost always outperform the double DM32 in this case, which is really interesting to see, except for this very laminar region in the beginning. So this also stresses the importance, and we will come back to that when we talk about the separators as well, that your borehole radius should be as small as possible to enhance the heat transfer to the fullest extent. Now, for the pressure drop, we have the following figure, where we see that the MuoviELLIPSE is actually worse than the single DM32. And the reason for that lies in this hydraulic diameter. So due to the shape, the hydraulic inner diameter of the MuoviELLIPSE is 24 millimeters when compared to 26 millimeters for the traditional circular probe. And this difference, well, of course it means slightly higher Reynolds number, slightly higher velocity of the fluid, so also a higher pressure drop, which is why the MuoviELLIPSE deviates from the single probe here as well. And it starts also a little bit sooner, getting a higher pressure drop, and that's again the price you have to pay for this turbulence and this better heat transfer. Now if we compare this to the solution or to the case with also the DN40, you see that the MuoviELLIPSE DN40 is, as said before, slightly worse than the single DN40, again due to the difference in hydraulic diameter, but it's performing way better than the single DM32, which is also in line with the discussion in the previous part. So this was what I wanted to say about the MuoviELLIPSE, about the model development, the boundary element method, as well as the CFD correlations. In the next chapter, we will be going over something completely different, the Gerotherm vario and flux probe from HK Gerdur, that are specifically designed to lower the pressure drop and hence the pump energy consumption in geothermal systems.